Great. So let's start the class. So just some recap of the things that we have seen so far. So we talk about game theory, the motivation, what is the one very important aspect of game theory is that when you have some kind of agents or selfish agents, you try to design some mechanism or some algorithm, but you need to consider the objective of each of them. And in some sense, it is a multi-objective function. And again, even the person mechanism designer can be a game player. You can have a different player with different powers, etc., which is very natural. Has applications in lots of places. And one thing that makes a lot of sense out of it is the concept of equilibrium. That in some sense, if the people are happy, if the situation around me does not change, I don't want to change. So that's a very natural thing. And of course, the issue that can be like by economists, this is the question that whether this converges to some kind of equilibrium, what are the properties of that, the structure of that, etc. That we are also talking actually in computer science as well, and the price of anarchy, etc. That we will talk about it, or price of stability. But the issue is that whether such a thing exists or not is important. And one important one was Nash equilibrium. There was this dominant equilibrium, but that was essentially very rare. So Nash equilibrium was the interesting thing that if all around me, essentially, the people don't change, I don't want to change. This is the one that makes. And this is the great result of Nash, that actually such a things exist, essentially for some kind of finite games. And we talked about how we can find an algorithm. The algorithm that we discussed, the properties we discussed previous time, and the one important thing is that you needed to essentially guess the support of this distribution, those places that you have this is because this exists only for mixed strategies, not necessarily for pure, it not necessarily exists. So you need to consider mix. And for the mix, you need to see what are the support of the distribution, which actions you will take it with probability greater than 0. You need to guess that one, but that would be essentially exponential things because you need to guess it. And that's essentially the hardness of the problem so far. And that's the reason that we discussed that this problem has been proved to be p-path complete, some kind of hardness. Still it doesn't say that we cannot find it. It says that there is a set of other problems like Nash, which are lots of them are fixed point theorems that we cannot actually solve them as well. Or like so far we cannot solve them. And somehow they have if we can solve one of them, then we can solve one of them in polynomial. That's all I did. Good. Now, so that was the Nash. So I wanted to essentially continue this line of essentially talking. Then we will talk about market equilibrium and other things. But before, I wanted to finish this one with some other one that actually are important one and we can compute. Another thing which is another concept that we are talking is the epsilon Nash. So what is epsilon Nash? So here the idea is that this is like the problem that you can also define other things. We say that in the Nash is that these people, if they say that this was the definition of Nash that let me bring also this notations. Good. Okay. So what did it say? It said that a strategy profile S is an epsilon Nash. Say it's Nash if you take any other action than your actions, Si prime versus Si, while the others keeping their things, you don't essentially gain anything. In the epsilon, I say, okay, you may gain slightly, just epsilon. And that's a very reasonable practical assumption. Why? Because you are in a good shape. For example, you have a house. You know that there is another thing that you can get it maybe a better price. You may not do that because there is some cost of changing the strategy. So if sometimes epsilon captures that fact that there is some cost of changing your strategy, and if it is the total benefit that you will get is just epsilon more, you may not do that. And the idea is that every Nash equilibrium, if you have a Nash equilibrium, epsilon is greater than 0. If you have a Nash equilibrium, then also you have epsilon Nash, because epsilon can be 0. So around any Nash equilibrium point, there are some areas that essentially epsilon Nash. Among those guys, if you are go around this, like if this is the point of Nash equilibrium, maybe around this there are some cases which are also epsilon Nash satisfied. But as you see, actually, is not necessarily correct the reverse. As we discussed, there are some places that all of a sudden becomes epsilon Nash, while they are very far from any Nash, essentially. Good. There are two reasons, as I mentioned. One is essentially the fact that epsilon Nash, like these kinds of epsilon, is just because of the cost of the change, you will capture it in epsilon. That's a practical thing. There is also another important thing. Because this Nash that we discussed, we didn't mention it is necessarily real or anything. I mean, sometimes it becomes. But anyhow, if we want to do it with computer, this computer have finite precision. So in some sense, if whenever we are doing that, in some sense, we are just getting essentially, when you compute it with machine, in some cases actually might be real, or like might be always real, essentially, might be some finite precision you can represent it when you do, for example, using linear programming that I mentioned, but not always. And the question is that, I mean, in that case, maybe if you have a finite precision, maybe that epsilon is the one that captures essentially the precision that you don't get. However, there is a third reason. The people say consider Nash, then it is p-path complete, then say that, okay, let's define some other concept, such that we have a paper or some essentially other concept. And of course, there are, I mean, I think well justified in this case. And maybe we can find at least epsilon Nash in polynomial time, or like something better computationally. But it's shown also, this was an, I mean, as I mentioned, discussed about this p-path complete result. There was a result that also showed that epsilon Nash also is p-path complete. So you cannot even find epsilon Nash. However, so that I have said, I wanted to give this other property. There is another issue that with epsilon Nash exists, that for every Nash equilibrium, there are epsilon Nash equilibrium that approximate it. But the converse is not true. So there are some epsilon Nash that aren't close to any Nash equilibrium. So as I mentioned, every Nash equilibrium you consider it generally around it. Sometimes it might be just this point, but this point itself is an epsilon Nash. So if we have this point, this is like, for example, this is the place that, so this is a Nash equilibrium. So around it, maybe it happens in some cases that this epsilon Nash, it just becomes this point. But anyhow, we know that the Nash is also epsilon Nash. But there are some places that are just epsilon Nash and not necessarily close to any Nash. And this is a good example, essentially, that I wanted to give it here. Good. So this is a good example for this. So consider this game. Essentially, these are two people, essentially player. This is a role player one. So this is a role player one, and this is a role player two. So in that case, and you have two actions, U, D, L, D. I mean, these are like, doesn't matter, because anything we can represent it, this kind of normal form games, as we discussed before. Now, here you can see that there is a one Nash here. Like you say, in terms of like, we are talking about the pure Nash, but you can also say about the mixed Nash as well. So here, what would be the Nash equilibrium is this 500, 500. It's like kind of obvious, because if anyone, this is so large that if you change any of these 500, you get 1, 0 or something like this. So that is a clear Nash. And as I mentioned, any Nash is epsilon Nash as well, because you just put epsilon, for epsilon 0, it works. Of course, it works for an epsilon greater. But another interesting thing is this point, this 1, 1. This one is, there is another epsilon Nash, which is UL. Yeah. So here, if you see that these agents, so if this guy is attaching essentially, say that I want to use U, if the other guy changes, it gets 0. So that is there. And also if this guy, but however, if this guy is speaking essentially with 1, this guy is changed, then this guy, if it goes from U to D, only gets epsilon over 2, not epsilon. So this is actually epsilon Nash, but it is somehow very far from any actual Nash. You can actually generalize this one for mixed Nash. You can write it down essentially, this one. And actually, you can say that there is only one Nash equilibrium here in this case. This is the unique Nash. This is something called ISDS. This is the approach that you can actually, if there is some dominant strategy or this, if essentially in this, the whole idea is that if some matrix are given to you, one other heuristic that the people are doing is that if some action dominant the other action, actually you can just remove that dominant, the one that is dominant. Or even if a set of actions dominant one action, you can remove that action that is dominated and continue. That's the way essentially it is called ISDS. This is some kind of more heuristic. Not that work all the time. But if you apply that one, you can show that always you can do that. And if you do that, you see that the only Nash actually becomes 505. So that's a unique Nash, but there is epsilon Nash which is far from. So in some sense, this is the case that epsilon Nash actually create other things. It becomes a bit more complicated. But at the same time, I mean, also it is p-pack. So that's one other concept. Now let's go to other ones, correlated equilibrium. That's another generalization of Nash that is actually very useful. So let me just so let's go. By the way, again, I emphasize that please, I mean, there are lots of videos about introduction to computational game theory in my YouTube that talks about it. So here I talk about some important ones because I want to create the content, and also you're just going in the high, like not some of them we go to the details, but just important one from that I want to continue for this. But there are several other things that you should know essentially, and these are important. And this is the one, like for example here, this is the irrationalizability that I don't talk about it here, but you should read it actually. So the concept of common knowledge, etc. All of them are, the video is there, you can just. Correlated. Good. So another thing that is actually very important is like another concept on this one, it is correlated equilibrium. So we just consider different equilibrium important. We talk about dominant one, dominant essential strategy and dominant equilibriums. We talk about Nash, epsilon Nash, and this one, it is very important. There are several others, but these are some important ones. Correlated equilibrium. So this is actually a quote from Roger Mason, who is actually a great economist, and he also got Nobel Prize. So he says this one, if there is an intelligent life on other planets, in a majority of them, they would have discovered correlated equilibrium before Nash equilibrium. So this is the thing that he claimed essentially. But this is actually useful things. You can use it for other things as well. The whole structure is the one that you can use instead of equilibrium, something versus another. It's the nice quote that I used it actually. Or I've used it essentially for other things as well. But anyhow, so he mentioned that. Let's see why he's talking about it. So, what is the okay? So What is a correlated equilibrium? So the idea is that we have some kind of traffic light. The idea somehow comes from the traffic light. That somehow is there. What is the role of traffic lights? It is there, and it tells the agents that what they should do with it. And you sometimes give them some hint that also, if you don't do that, then the result can be catastrophic. It means that essentially you make, this is like, here, when the light is green, if the one that is a red light, if you pass it, there's a chance that, you may die. They have seen even like accident just on these cases that was very bad accident. So instead that if you don't do this action that I recommend, say that I will say stop, the other ones that you can go and vice versa at any time, then the result can be catastrophic. It means that your utility can be very bad. This is somehow the idea. And it is interesting. So every correlated equilibrium, like every Nash equilibrium is a correlated equilibrium, but not vice versa. Not every correlated equilibrium is a Nash equilibrium. And as I mentioned, what are the benefits is that there are several things. First, is that like maybe from computer science point of view, is that we can compute it essentially, a correlated equilibrium in polynomial time, which is actually good because in particular about this one is that we are suggesting the actions to the people. And said this is like traffic light. Traffic light works, so it is important to actually compute this and give it to the people. And if you don't do it, it is catastrophic. So computation is important. Other things are important. You can do some kind of fairness. Like you may decide, essentially, mechanism designer may do something because not now these two players are there. There is a God that decides, essentially, God or traffic light or anything that decides that these are the actions that you should take it. And I consider some measures of fairness and also maximum social welfare. The social welfare can be more essential. A good example for this is this one. So if you see that, like in the correlated equilibrium, this is the three games that we discussed previous time. We talk about them. This is like essentially battle of sexes. We talk battle of sexes, prisoner's dilemma, and matching pennies. These are like three important. So if you remember this, and as I mentioned, this is the normal form game. So any games independent of what we call, you can just represent it by this normal form. And for this one, we had a mixed strategy. Nash equilibrium. What was that? This is a mixed Nash, essentially, and we showed, we discussed how you can find it. Again, guess after guessing the support of these distributions, which is exponential, then you can do the rest with linear probability. So you can say that this is essentially this is for wife is going so wife is doing 2/3 opera and then 1/3 football. This is the distribution of probability. And what about for husband? It is 1/3 and then 2/3. Good. So then when you have this one, then you just compute the landing probability. That is the one that we discussed. For example, what is the chance that this guy is doing this one would be 1/3 times 2/3. So you can see that essentially this is like, for example, for wife, let's compute it. So for wife, what is the expected utility? It would be 1/3 times 2/3 times 2. And here, so would be 1/3 times 2/3 times 2. And then 1/3 times 2/3 would be 1. So what's the meaning of that? It means that 5/9 of the time, because 2/9 here and 2/9 here, they get essentially 2 and 1. The rest they will get 0. And if you compute it, you can say that each agent, both of them essentially. So this is no coordination here. The correlated equilibrium has coordination. Here there is no coordination. It is fair, yes. Both of them essentially get the expected utility 2/3 in some sense. But lots of the time, actually, like for example, here 4/3, and again, if like with 5/9 of times this probability 5/9, they essentially come into this area, which is 0 for them. It is fair, but it is again. Good. And the idea is that, so somehow it seems a bit, maybe, not optimized. They can decide another way. That is the whole idea that the concept of correlated equilibrium is coming. That instead of doing this, why they don't do just do a randomization between these two options? Essentially, toss a coin. So either we will go to opera or we are going to football. And then each of them gets at least one versus, 2/3 that they got it, and everything is better for them. That's a whole concept of essentially correlated equilibrium that we try to decide that maybe they can do it. And this essentially talks about the correlated, the concept of correlated equilibrium. And we will see actually this correlated equilibrium is indeed a generalization of Nash equilibrium. So why is it first intuitively? What is the main difference between this and Nash equilibrium? Is that in the Nash equilibrium, as we discussed, for example, we put it 1/3 here, 2/3 here, and then the landing probability of each of them was essentially 1/3 times 2/3. In some sense, I will call this one landing probability in each of these cells. The landing probability for each of them, you could write it in terms of multiplications of two numbers, two probabilities. In correlated equilibrium, we compute exactly the same thing, the same things, but the probability that we obtain is not necessarily can be decomposed into like a strategy for wife, a strategy for husband, or the first player, second player, such that this landing probability is just multiplications of this. Of course, if the landing probability is the multiplications of this, then it is a correlated equilibrium, because in both cases, note that the sum of the landing probability over all cells, all situations, should be 1. So in both of the cases, it is the case. For Nash equilibrium, we can decompose it into multiplications of two probabilities. In correlated equilibrium, not necessary. And that says essentially correlated equilibrium is more general than that. So in some sense, Nash equilibrium is good because these guys are independent. They can just do independent whatever they want, essentially, and it is the case. But in some sense, as I mentioned here, for example, they can do better correlations and do that. So if this kind of one-shot game that they don't know about information about others, there is no other coordinator that they trust, no God or something like it that they trust, then in that case, they may actually just do Nash equilibrium. But Nash equilibrium, it's hard to find in polynomial. So let's, again, these are the things that I have mentioned, just some formulations. In the correlated equilibrium, we have these things that, this is the simplest case, you can generalize it more. Say we have a two-agent game for now. In the mixed Nash, as I mentioned, you can compute a probability matrix. This probability matrix, P of ij, landing probability for each cell, can be represented as Qj and Q prime j, Qi and Q prime j. So you just consider for each guys, this is essentially so this is ij, and this is P of ij. So for P of ij, you can just say that this one is equal to qi times q prime. You compute it, and you are good to go, essentially. And you know that, of course, here, because it's a probability distribution, some of these qi's are equal to 1, some of the qi's are equal, q prime also equal to 1, and also some of the landing probability is equal to 1. So here, if we remove these conditions, that Pij is equal to this one always, so if we don't have it, then Qi and this one also does not make any sense. But still, we have this property that sum of this probability over the whole action sets, all the cells, or essentially action over all action profiles that we discussed. Action profiles means the sum of these cells. Then it would be essentially, is a relaxed version would be Nash equilibrium. It would be correlated equilibrium. So we can always say that, I mean, essentially correlated equilibrium, like every Nash equilibrium is a correlated equilibrium, but not vice versa. We will see also in terms of formula. And for n-player games even, we can compute correlated equilibrium as long as the size of this cell essentially is polynomial. But we cannot, I mean, so far we cannot solve Nash equilibrium in polynomial time. And the main things that makes it hard essentially is this property, that this is the main important things that we have it, that in some sense in Nash equilibrium, this Pij is decomposable into multiplications of two probabilities. Let's see the So let's see the actual LP that we can do it. Using Nash equilibrium. I just good. So how can we compute essentially this function? This is for correlated equilibrium. This is essentially the LP that we are writing for that. So one, we have this one, the probabilities. So what is A? A is any cell of this matrix, normal form game. A is the action profile. If you remember, action profile means all the actions, essentially multiplications of all product of all these actions. It means that essentially corresponding to the cells of this normal form game. So for any cell, the probability should be greater than 0, and the sum of the probability should be essentially equal to 1. The only non-trivial condition is this condition. What is this condition? It says this one. If you consider for any action, from any action profile from the set of all action profile, essentially for any cell, that AI belongs to that, like essentially that this particular action of like if you consider this one, this is the action profile, and this is the in this action profile or in this cell, agent I has done AI. It says that like if you sum it up essentially over this, so for all of this, so for each of them, what is the probability that this guy is doing that? The probability that this guy is doing this cell times the utility that I gets it with the action AI, because A here includes AI. If you sum it up over essentially all that, essentially this guy can take this action or this action and this action, etc., then sum of this should be greater than P of A, the same cell essentially, U of I, the utility that gets with the different action. So for example, here, if you consider this one, for example, if you consider all this, for example, these columns that All others are taking, so all others are the same. Just this guy can take different actions, correct? When it can take a different action, it says that if it takes the action prescribed by this, the one that is obtained by this, and essentially by this probabilities and the action that you get it from here, this action that it gets should be greater, the utility, expected utility should be greater than or equal to any other action that he or she gets it during this. And here, in some sense, when we talk about this, what do we compute essentially in the Nash equilibrium, in the correlated equilibrium? So the variables of this, essentially, all the UIs, etc., all of them are just some constant or something there. The only variables that we have are the PAs. What is the probability that you are doing in each cell? For example, if you remember in that case of husband and wife, it's essentially it puts 1/2 here and 1/2 here. It means that with probability 1/2 you will go here, and with probability 1/2 you will go there. If you take these actions, this is like either you go there or here. So it prescribes what are the actions that you should take. Or like if the run might be, I mean, here is 0 means that you should not take these actions, and you should just take this action and this action, this is probability. So it's something that's traffic light, but a bit more general, also gives the probability. Traffic light is just give probability 1. And for some cases, maybe the probability can be none. What are the good things about this one? The good thing is that this variable, we have this variable pi and this constant. These are just constant. But now the good thing is that here we don't have any objective functions. So we can find an equilibrium, we can have several of them. In the Nash equilibrium, just putting this essentially was done. We couldn't put that much on, because we couldn't solve even Nash equilibrium. But here, we can solve this one. Now you can find actually the one that maximizes the objective function. What is the, so for example, one interesting thing is the one that maximizes the social welfare. What is the social welfare? It says that you go there, you want to have lots of, maybe there are lots of probabilities that we can put it here. Find the probability ones that maximize the social welfare. What is this? It says that go to every cell. What is the landing that? In that case, what would be the total utility that these guys, all of them are getting it? Just sum it up and then sum over all matrix. That's essentially put the probabilities such that when you go to each cell, what is the chance that we are landing in this cell? And then what would be the utility of all actions? That's the thing that we do the sum and then sum it over all things. So that we can also optimize. And because this is a linear constant, we can put it and we can optimize it. So in that sense, actually give more benefits to us. Good. So let me also, I mean, this is also one thing that I wanted to mention. This is, I mean, why from this formula, every Nash equilibrium is a correlated Nash equilibrium. So this is the formula essentially that. Yeah, so this is, I mean, simple thing that why is any Nash equilibrium is a correlated equilibrium. So let's epsilon be essentially a mixed Nash equilibrium. I want to see why this formula also essentially from this formula I can do that. So if a sigma is a mixed Nash equilibrium, you will consider pick any AI which is in the support of this distribution. So consider just as those in the support. What do we have here? Essentially, we have these things that. So what does essentially Nash equilibrium says that? It says that if you consider if this guy is taking AIs, and so the whole action of this guy would be essentially A. So the whole action of this guy would be A. So if this guy is taking these AIs, it says that because this guy is taking AIs, so like some of the things versus like when all of these other guys, you can choose other options. Some of the sigma of so this is the probability. So what is the probability that the people taking the other actions times the one that UI gets it? It should be greater than the one that if like AI takes a different action A prime I. So this is essentially comes from the definition of Nash equilibrium. Now, we just multiply both these terms. So this is the expected. Say in expected, you should get essentially more than any taking any other action. Now, if you just multiply both of them by sigma of AIs, then actually, because we have this property that in Nash equilibrium, so the PA is equal to just multiplications of these guys, then this becomes essentially sigma of A. So in that case, if we set PA is equal to this, then it would be this, sigma of AI PA times this should be greater than this. And this is just essentially equivalent of the one formula that we had it on the the previous slide. It says that sigma of A belongs to A, that AI belongs to A. This is the exact formula that we have. These two are equivalent, essentially. If you just do that one, that would be greater than anything if you take it with different actions. So essentially, because we have this property that PA is equal to that, this is a Nash equilibrium property, we can just multiply this, we just write the Nash equilibrium, multiply it, and then we get some equivalent things, which is the one that I have mentioned. The LP, this is the LP that we know. And again, this is the whole thing. It computes some probabilities that you should just do it this one, but everything is correlated. And this is something that the nature or God or something computes and give it to this. So that's about the correlated equilibrium. And now let's go also to some other things. Okay. Another concept that exists essentially about min-max and maximin equilibrium. And essentially the zero-sum game. Good. The max-min or min-max equilibrium. So again, just consider this game a wife and husband. So for agent I, the worst case expected utility, which is a strategy SI, which is the minimum over all possible combinations of strategies for the other agents. Good. What is the worst case for me? What is the worst case? For example, here, if you want to compute what is this one for agent I, is that what would be my minimum essentially? What would be my minimum payment or utility that I will get it if you minimize over all actions of others, essentially? I think this is S minus I. So over all actions of others, what would be the worst case? Now, let's compute this one for this battle of sexes. Say that, I mean, this guy, the wife, is doing with probability P and 1 minus P here, and Q and 1 minus Q here. Good. Again, you can compute the landing probability. This would be the utility of the wife. It would be 2 times PQ because PQ is here, times 2, and then you will compute each of them, and that would be the good. Now, this is a trick that you can actually do it, and this is like a typical trick. So for a fixed P, if you consider fixed P, P is a constant, then in this case, this is linear in Q. If it is linear in Q, then, for example, if you put it P equal to 1/2, this would be equal to this in terms of Q. And Q is also between 0 and 1. So it means that the maximum or like the minimum for this should happen in one of these boundaries. Because as I mentioned, if you fix P, it would be linear in Q. If it is linear in Q, so is that the maximum or minimum, it should happen in both of either Q equal to 0 or 1. So we will do this one. So essentially, we will do this one. We computed essentially what would be at Q equal to 0 and Q equal to 1. If you compute it essentially, it would be like this. So because you know that the maximum would be or minimum would be at essentially either boundaries, then you can just put Q equal to 0, Q equal to 1 in this formula. And then you get this. You get this formula. So the minimum Q. So now for all over mixed strategies of essentially wife, that is based on Q now, the minimum that wife can get it would be minimum of these two guys. And again, if you want to actually compute the minimum, that would be what would be that, then you will put these two are equal, then you will find what would be P essentially. Now, what is the Maximin strategy? A Maximin strategy for agent I. This is a strategy SI that makes I's worst case exhibited utility as high as possible. So what is the thing that I'm doing that? I will say that, so for a person is that I don't know what is the strategies of the others. I will take an action that my minimum would be as high as possible. So that the minimum that I will get for SI, this is again, so this is S minus I. So this is the argmax of SI. So the argmax essentially gives the action. I will take the action such that the others, whatever they will get, my minimum is maximum. And essentially here, this is the max, this is called Maximin or Maximin essentially. And this is a security level that I know that I will take the action, whatever they are doing, I do it essentially this. You can say the same thing for players 2 as well. Let's see whether this is the case. So let me just check whether this other one also has this property. Not just this. Anyhow, so this would be, I don't know why there's some font issues. So essentially, this is a definition. And so that you can define it for player 1, you will say, what is the maximum that I will take it, while the minimum that I get, whatever the other agent gets, is essentially maximized. And this can be defined also for more than 2 players. It can be for n players. So that this is what is the maximum action that I get it. If everyone else is doing whatever they want to get it to together collusion, I have at least this security level. Good. Now, for example, here we computed essentially this one, that for wife, this is like the thing. So this is the minimum Q that this one. So this is essentially the one that computed for other agents. And we know that this is the minimum. Now, to find essentially the equation for husband here, actually, because this is the minimum is this one. Now you know what is the formula. Now here it is Q. Now you need to say for P. What is for husband? For husband, the one that essentially that minimum is maximized is just putting these two are equal. 1 minus P equal to 2P. That gets P over P equal to 1/3. So good. So in that case, you can compute it that, for example, the wife Maximin value would be, with the case that P is equal to 1/3 and 1 minus P is 2/3. Similarly, you can compute it for other, but you just compute the formulas they mentioned because it's linear, you know that, and then you take the other actions, the other guys. This one you put them equal. These are like basic algebra. Then you will compute the best. So you can say essentially for wife, the Maximin strategy is 1/3 opera, 2/3 football, but for husband is 2/3 opera and 1/3 football essentially. There is the same concept min-max. What is this one? This is the one that's essentially the dual of max-min. It means that a strategy, this is a strategy that agent one wants to punish agent two. I want to take action, I don't care essentially. Sometimes I don't know, they call it terrorist activity or like terrorist action or something like this. You want to essentially hurt the other, independent of the thing that happens to you, to the player. So in that case, agent one wants to punish agent two. He says that I will take essentially an action that the maximum for the other guy is minimized. Good. So I will take an action that the maximum that the other guy can take it is actually minimized. This is exactly the reverse of it. This is for two players that we can just divide it. Good. So, so you can define essentially for two-player game that is very easy. So this is essentially min of S1, S2 that you can just define for S1 or S2, and arg mean essentially the action that you are doing. So one is essentially that you take the action such that your minimum is maximized. That for max-min. For min-max, you are doing this. I will take the action that the other agent's maximum is minimized. Now, the question is also, so you can compute it, this very similar to that one, you can compute it, the same role that I have mentioned. I don't go through that. You can go to the videos for this and think that. But also you can define this one actually for more than two players. But then the question for essentially, what is the idea for more than two player is that everyone else gang up, because for two is clear. I will do for you, you will do for me. But what if more than that? What's the meaning of minimum? This is the concept of gang up. So it means that everyone essentially, all others are gang up against for one particular agent. So what is essentially, this is the, here if you want to, so let's S star minus J be the mixed strategy profile that minimize J's max-min payoff, that you will take it over all other actions. They can together essentially that can gang up and hurt this guy. Then essentially you will take the minimum of these actions essentially. So here essentially this is the definition. So you are taking essentially the these other guys, all these other guys, S of minus J means that all other guys, they gang up such that the maximum for Sj is minimum. That's essentially, you can generalize it. Good. Now I wanted, why did I mention that? Because this is also this kind of max-min and min-max. These are some kinds of essentially game theory concept, essentially, some kind of equilibrium concept, some kinds of concept in game theory. And the most important things here is this one. This is the Minmax theorem. That is the von Neumann 1928. He said that if this is another equilibrium, that this is another case that we can compute actually Nash equilibrium in polynomial times. If G is a finite two-player zero-sum game, what's the meaning of zero or constant? Zero-sum means that the sum of these two guys, or in general, constant sum means that the game that might be multiple players. But in all of this, the sum of the utilities, it might be different for different people, but the sum is the same over all cells. And in particular, zero sum means essentially some of them are equal to 0, and these are equivalent. But it said that if we have a 2-player zero-sum game, then you can say that i's expected utility in any Nash equilibrium is equal to i's Maximin value and i's min-max value. So what's the meaning of that? It means that if you have a Nash equilibrium with S star, like Nash equilibrium, the strategy that you will take it in Nash equilibrium is the same strategy that you want to minimize, you want to maximize your security level against the other one. Also the same strategy that you will take to hurt the other guy. That's the meaning of essentially the theorem. All of them would be the same. But if it is not a constant sum game, like for example, as we have seen in husband-wife thing, it was some places like 2 + 1, the other ones were 0. It is not a zero-sum game. But anything that I lose, the other one. So the sum is not always equal to 0 over all cells. Then this theorem does not hold. And also, if it is a constant sum, but the sum is also like the number of players is more than 2, also this theorem does not work, and this is essentially the property finding the Nash equilibrium even in those cases would be hard. So only for 2-player zero-sum games we have this one. And why do we have this one? Again, because this is another one that I wanted to cover. This is another one that we can find it polynomial. How, again, using LP. So essentially, any time that we can solve it is the LP. Let's see how can we do that. Let's here. So U1 is U. This is the utility. Because it is a zero-sum, 2-player games, U2 would be exactly minus U1. Or U1 would be equal to minus U2. Because anything that you will get, the other guy should lose. It is called pure competitive, essentially. These zero-sum games, pure competitive games. So let's consider a mixed strategy. This is the probability distribution for the first guy. So S1 is equal to X. The strategy that I will take would be X1 to Xk. And for S2 would be equal to Y, which is Y1 to Yr. And say this player, first one has K strategy, the other one has R strategy. Now, what is the utility of xy? So essentially here, what did we define? We have just defined this one. So this is x1 to xk for the first player, the row player, and then this is y1, y for the second. Now, what is this one? Essentially, it says that go to each of these cells. Xi, xj would be the landing probability times the benefit that uij. Good. And U is, everything is U. We are talking about the first guy, person. Now, what do we want to find? So here we want to find X star, which optimizes this V1. What is V1? It's, what was the Maximin? It is the maximum X that you want to get a probability X, the strategy, that minimize over all possibility that the second guy. That's essentially the Maximin definition. Now, this is just these two lines. These are like, I mean, interesting. I mean, these are tricky and I mean, interesting actually, not that complicated. But if you don't consider the right angle, it actually might be hard to get it. So here we know that since player 2 is doing his best response, good. So like here, this player 2, anything that you will get X, then this X is fixed here. Then this guy is doing essentially the minimum that he can get because he wants to essentially minimize for this. Whenever he sets Yj greater than 0, if it takes anything, Yj greater than 0 means that anything which is in support of this second distribution Y, this part Xiuj, it should be minimized. So here you see that this Y, guys, this is come from this formula. So he said that it tried to minimize this thing essentially for the guy, for the first guy. So whenever he like the second player decides for yj, whenever he takes the yj, it means that yj greater than 0 support. This should be minimized. Why? If not, then it can move this yj to the other person, to the other ones, which is less than that, and essentially gives a worse utility for the first player. So whenever it is in the support, this xi uij is minimized. This is a very tricky thing. We are using this trick a lot. I mean, in some sense, we use also this one for Nash equilibrium. So it means that essentially, when you take it, anything in your strategy in the support, they should have the same essentially utility here. Now let's write this one. So what was V1? V1 was essentially this formula, Maximin. So you want to, this is the V1 essentially, you want to compute it for this one. So V1 in this equilibrium case that he has it is equal to sigma j yj. This now, because of this fact that I have mentioned, so here we were considering essentially x star that optimizes, and then we optimize this. So it means that this is like essentially this is the one that we are writing this one for the x that essentially optimizes. As we mentioned, because this formula that I have mentioned and this fact that whenever yj is greater than this, this should be equal. It means that all of these guys, so here essentially, we know that, so here, all of these guys should be equal because of this thing that I have mentioned. So we can actually factor out this one out and then just sum it up, because all of them, this was essentially this yi. I mentioned that whenever this yi is greater than 0, this should be all equal. So it means that this minimum among them, you can take that minimum out and then just sum it up all the yi's. But some of the all yi's would be 1. So it would be essentially this would be equal to min of j, this one. And this should be, so V1 is the one that does this action essentially, is being maximized. This should be less than for any other essentially j we have this property. This is just simply by definition, correct? Because we know that the min of j over this should be less than or equal to xij, because that is the definition of min. So here we obtain that the V1 should be the mean of these guys, and we know that this should be less than this for any j. Now, how can we write the whole things? So here we want to write one essentially V1 for the first player, and the strategy x with the strategy x star, which is optimum, and we want to maximize V1 because that was the definition. So that was essentially the one that we want to maximize V1. What is the property? We know that V1 always should be less than xi uij. This just comes from this formula that we have mentioned. So this is just this formula that we obtained it. So we want to find a V1 that satisfies this property. And then some of the xi's are equal to 1, because the sum of the probability should be equal to 1, and xi is greater than or equal to 0. So this is essentially for Maximin. Exactly like that. We can also write it for Minmax now. Like exactly the same formula, the reverse of it, we can write it down. If you want to consider the min-max, that would be like this. This would be the formula. So this would be for the V2, you want to compute min-max. Then you want to minimize this. The only condition is that instead of there, we say that V1 should be less than this, this should be greater than this. And this would be essentially for player 2, because that is, we are doing for a different player in some sense. Then sum of the yi is equal to 1 and this one. Now, So we have these two LPs, and these two LPs, actually, this is the one. This LP, this second LP that we have it here, is the dual of this LP. This is the duality theory. I mean, you can just do that. This is a generalization to call KKT for nonlinear programs. But because of the duality, and this is the duality theorem, duality theorem has several names. It calls it also Minmax theorem, the same one and things. Or it calls Farkas lemma. All of these three names are the same thing. And essentially, it says that here, this LP, because this other one is the dual of this, or this, essentially they are dual of each other, their value should be equal. So here, and note that here we have used both of these properties. This is the zero sum when we have written this formula essentially here, and this is a two-player game. So for two-player games, I mean, this the proof of min-max, or like this essentially, like one way is easy essentially. Why you can see that like the V1 is less than or equal to V2. Because V1 is essentially just the it's just one, like, you know, when you try to, for example, here, when you try to minimize this one, V1 would be just one set of action that you will take. Of course, that arbitrary action, a feasible action, would be less than the optimum one. But why they are equal, they come essentially from min-max theorem. And again, it is called min-max theorem, Farkas lemma, or duality theorem. And this is essentially that von Neumann. He said that these two LP have the same value. And because of that, one is essentially max-min, the other one is min-max. And also you can show that this is like, that is also easy, that this also satisfies the Nash equilibrium as well. And all these three of them essentially can be obtained in polynomials, like min-max, max-min, and Nash equilibrium. For zero-sum games, two-player games, we can get it. But even it is like zero-sum, three-player, then we cannot compute it. Then the problem becomes hard. It becomes as general as possible, because this zero-sum, essentially the third guy, you can have a dummy guy that makes everything equal. So if you have a three-player in some sense and the constant sum, then it is essentially equivalent of two-player Nash, because you can always have other, essentially intuitively, you can have one other player that puts makes anything that these two are not equal, just this guy essentially makes it equal, and essentially, so three-player constant sum or zero sum does not help you for anything. And essentially as hard as Nash, and it is big enough. Great. So that's essentially these 2-3 other, like the cases that we can solve Nash in polynomial time we discussed, correlated equilibrium, epsilon Nash, etc. that we discussed. These are some of the things that actually talks about Nash equilibrium and try to capture them well. So we will talk more about this. As I mentioned, we talk about this Nash equilibrium, other structural properties of Nash equilibrium, for example, for price of anarchy or price of stability, as well as later for market equilibrium. And then also we talk about auctions in this course and the important cases there. That's something that will come later in this course as well.